Hey, welcome to our discussion about planar graphs. So first let's start with the definition. A graph is planar if it can be drawn on a plane surface with no two edges intersecting. We sometimes say that the graph is embedded in the plane. We will see some examples about the planar graphs, and the first one is K5. K5, as you know, is a complete graph, and usually we draw it like this. It's a star shape with all nodes connected to each other. There is no way to embed a K5 graph on a plane in a planar way. So you can try this. You can, for example, try to draw this outer pentagon and then put some inner edges. But at some point, for example, you can draw this edge here from the outside. So you don't have to draw this. And then this edge can be, for example, drawn like this instead of drawing inside. But still, there will be another cutting edge here that prevents the graph to be planar. Here, we will have this discussion later, but you see basically a donut shape, which we call torus. We show that actually K5 can be embedded on the surface of a torus. So here are some examples. This graph here, which is K4, is embeddable on the plane like this or like this. Cube graph, which you see here, is actually planar. We can draw the same graph like in here. So it is planar. How about the graph below? Try to find out if you can draw this graph in a planar way. Let's define the faces. Faces or regions are defined on a planar representation of a graph. So when you have a planar graph like here on the left side, it divides the plane into a number of connected regions, and those connected regions, like here or here, we call them faces. So here's F1, here's F2. Each of these are different faces of a planar graph. You can see that F1 is a little bit different because it actually covers the outer area. It seems like it's not bounded like the other ones, but actually F1 is also bounded with the outer edges of the graph. So each face is bounded by edges. One of the faces encloses the graph, which is F1 here, and we call that type of faces exterior face. We can draw the same graph like on the right side. So basically you can have different planar representations of the same graph. And here on the right side, you see that F6 became the exterior face. Probably the most important and most famous theorem about planar graphs is the Euler's formula. Euler's formula says that there is a connection between the number of faces, number of edges, and the number of vertices of a planar graph. And that is the Euler's formula. You can see it here. The number of nodes in a planar graph minus the number of edges plus number of faces is always equal to 2. The degree of a face is defined as the number of edges bounding the face. If we go back to our example here, let's try to find out the degree of F4. We need to count the number of edges on the borders of F4. So 1, 2, 3, 4, and 5. The degree of F4 is 5. You can find the other faces degrees by yourself. There is a simple relation about the number of edges, total number of edges of a graph, and the total degrees of a face. For any simple planar graph G, we have this relation here. The number of edges multiplied by 2 is equal to the total of all degrees of faces in the graph. Please verify on the previous example here this formula. There are some corollaries to Euler's formula. For example, for any simple connected planar graph, if the number of edges is greater than 2, the following inequality always holds. The number of edges is always smaller than or equal to 3 times the number of nodes minus 6. We will use this formula later to assess the planarity of simple graphs. This slide shows you how to find out or how to prove that K5 and K33 cannot be planar. I'm going to explain K5. So we know that K5 has 5 vertices and 10 edges. Inequality of the corollary 1 is violated here, because if you look at corollary 1, in any planar graph, number of edges cannot be greater than 3 and minus 6. If you replace these numbers here, number of edges 10 smaller than or equal to 3 times 5 minus 6, which is not true. Since this inequality is violated, K5 cannot be a planar graph. Try to find out whether why K33 cannot be planar. Now, let's talk about the differences between a sphere and a torus. Again, remember, torus is a three-dimensional shape which has one hole. Typically, a donut is a torus. So K5 and K33 are said to be toroidal graphs because although we cannot embed these graphs as planar on the surface, we can embed them on the surface of a torus. The reason is that sphere and torus are topologically different. Why is this difference? Any single closed line, that is a curve, embedded on a spherical surface, divides the surface into two regions. A closed curve embedded on a toroidal surface will not necessarily divide it into two regions. You can see it here. For example, if I draw a circle, think about the sphere as a three-dimensional. Try to envision it as a three-dimensional solid. Then any circle you draw on the surface will divide the surface into two regions. However, on a toroidal surface, you can, for example, create this circle here. This is the back side, this is the front side. The torus is not divided into two regions. It's still one region. You need a second circle to create two different regions.